All right, my friends, we're through most of it. It's all happening. We had almost 2 complete full days of Spring One, and my daughter's ready to talk to me. Sweetheart, I'm on my call. It's the last one, so give me a second. And we've got two of my favorite people on the planet giving a great talk about hashtag Bootiful time. So please, everyone, welcome Josh Long and Mario Gray.
Thanks, Bob. Love you, man. Hi, everybody. Thanks for joining us today. We are super excited to virtually see you all today.
Hey there. This is Mario Gray.
I'm Josh Long. Thanks for joining our talk today. We're going to talk about concurrency. We're going to talk about threading. We're going to talk about building systems that optimize for high availability. And so when we talk about this, several things come up. One is, how do we make our systems more available? And we're going to take advantage of concurrent programming. We're going to talk about multi-threaded programming today to make that more possible. And of course, when we dwell on this topic, some things obviously spin up, some things arise from this discussion that we need answers to, things that I'm sure all of you are thinking about as well. First and foremost of which, what is the male equivalent of a seamstress? We didn't know. There's a lot of different words. I thought this was a thing that you would probably want the answer to as well. So we Googled it because I knew it was a seamstress, threads, all that kind of stuff. I didn't know, is it like a seam? I don't know. So we Googled it and we found sartor apparently is another word. It's a more of an English UK definition for a seamstress, right? Or for tailor. So that points to the word tailor. And then a seamster is also a person who sews and does tailoring. So Google was smart enough to point us to two different definitions that both in turn transitively link to the word tailor. So I guess you could say that the male equivalent of a seamstress is a tailor, although I think you can have, could you call a woman a tailor as well?
Probably. I probably would too.
Yeah. So this is just weird. We didn't realize it was a separate, it's a whole thing. Anyway, Google was not smart enough to do that for us, but it was smart enough to follow us on the internet and predict that we'd be speaking at Spring One. Don't know why. This is not a thing that we liked. Anyway, threading gives us the ability to make highly available systems, right? We like that. We want our services to be available. We want them to be responsive, and that's very important. Users like highly available systems, and they like, or at the very least, they like the perception of a highly available systems. So we are, we need to take advantage of threading in our system to do that. And it's not a new thing, right? Obviously, threading has been available. Multi-core, multi-CPU, multi-threading CPUs have been around since the 1950s. So we've had a long time, a lot of history of people building upon multi-threaded systems to deliver better services and software. 70 plus years have gotten us to this point, generations and generations upon generations, building on each other to get us to this point, right? Obviously, a lot of stuff has been done to maximize the potential of computer hardware. Obviously, it's not magic though, right? We are still at some point limited by CPU availability. We've got a lot of things that we can do in our current computers, right? Today, machines have a lot of cores, right? A lot of potential. For example, this machine on which we're presenting to you right now has 16 cores. That's crazy, right? That's crazy. The potential is limitless. It's endless. And so, it's hard to imagine that we got to this point, to this juncture, at this point in history, with so much capacity, so much potential at our fingertips, and we can finally, Mario, run Slack. Oh no, we cannot. We can't run Slack. What is going on? I did not see that coming. I thought we would be able to run Slack at this point, but as this graph by Matthew something shows, not really. It's not a thing. Look at that. 74% CPU time in total across all those different CPUs on this person's desktop. So that was antithetical. I didn't see that coming. I don't know how we got there. We didn't really get there at all, did we, Mario?
I don't know, but no, we didn't.
We didn't get there at all.
We're still here, though. What are you trying to say, anyway?
I'm trying to say computers are a mistake, and we should just boot directly into Slack. It's clearly not going to work. No, you're right. That's not what I'm trying to say.
Okay.
What I'm trying to say is we have a lot of potential, right? If we just fully leverage the machines that we've got, we can do some amazing things. But that said, we have to write code that takes advantage of that concurrency, that takes advantage of the hardware, right? And there's some inherently complex things in there. There's inherently complex control flow that we need to worry about. It's hard to coordinate multiple independent actors in a system. It's especially complex when there's shared mutable state or even non-shared mutable state, right? You have all sorts of tricks that you have to do to have the illusion of control. Things like transactions. Now remember, not everybody likes transactions. You think your transactions are your ally. You merely adopted the state machine. My threads respond in it, molded by it. So things are difficult.
Things are very difficult, actually. It's difficult to get threading coding right the first, second, third, or fourth time, or even the nth time. So basically what I want to say to you is, here is a gentle reminder. You don't know how to code threads the perfect way. Nobody does. There's actually truly only one person who really understands how to write safe concurrent code. And it's not you, it's not me, it's not anybody that I know of. And what I truly understand is we don't know who it is. But here's the lesson. This is a message for hope. This is a foreboding warning. Try not to write threaded code whenever you don't have to. So in this talk, what I'm going to try to do in our first demonstration, I want to take the edge off of threading. I want to show that threading is approachable. Threading is something that everybody can do. Everybody should be able to feel comfortable with without getting into the nitty-gritty and the weeds of threading. And what we want to do is also make sure that threading is also testable, because it's one of the harder things to do is test threaded code. I don't like writing threaded code test, but I do like writing code. So we want the benefits of concurrency and testability. We don't want to sacrifice the readability, right? So buckle up. Let's get ready to code. We're going to test those threading tires. And the first thing we're going to do is we're going to show you a little bit of what Spring can do to help us write better threaded code. And in that, I'm going to use something called Spring Boot that allows us to write concurrent jobs and execute them on, schedule them on the CPU. And we'll do that by going to my favorite place in the whole entire world that's not production. What is your favorite place in the whole world? Yours is production. Okay. Well, I like start.spring.io.
So that's my second favorite.
Yeah, I know. It should be our first favorite place. You know, it's only been my first favorite place since I was born. So let's go ahead and add a Java project that's Java 11. So we're going to use some of the advanced Java 11 features. We're going to use Lombok because we love Lombok. And I will generate this code base and I will open it up so we can drive this. I spelled it wrong, but that's okay. We know how to spell async. It's actually A-S-Y-N-C, not A-C-Y-N-C. But if you try to spell it with A-C-Y-N-C, nobody's going to bother you for that. Okay, so let's go ahead and enter and explore. What I want to do is, I had an idea. So I had this great idea of doing transcoding. I've done some transcoding in the past. I want to do some transcoding again.
You need a demo.
Yeah, we need a demo. We need something to show that we can get off the main thread and do some work. Yeah, but like, okay, so what we want to do is we want to make so that the clients are able to process other things in the meantime. And so we thought about this. We thought about what's going to tax the CPU.
Slack.
And I had this idea, and no, we're not going to run Slack. Don't make me get the hose out. Okay, how about FFmpeg? Okay, so FFmpeg is great because it's a CPU-bound process, and it's like one step better than thread.sleep. I feel like we owe you a little bit more than thread.sleep, so give us some credit here. We're running something called audio utils that we wrote in the background. We're not going to write it here because it's just a little bit of forking, doing code in the background that isn't necessarily, yeah, it's going to take time to write. So we have it right here, just ready for you. Yeah, it takes time to run. Yeah. Okay. So here's our async util, and what this is going to do is essentially it's going to fork a process out, and it's going to do some processing with FFmpeg, just like we said, but it'll join that process back into our Java process when it's complete. And that's the type of action that we're looking for in this case. And it'll basically lead us naturally into Spring integration. So for now, we're going to use an asynchronous thread. And in order to do that, I will create a bean. And I will say, how is this going to work manually? So I'll call it, let's see, class. I'll say async. Actually, the first thing I want to do is I want to do a service.
Interface. just a class. No need for the interface.
Thank you. I know. I mean, don't make me get the hose out. Yeah. Audio service. So what we're going to do is create an audio service. And this first audio service is simple. It's going to essentially say, I need an executor, and I need to be able to, hi, thank you. So I need an executor. And so what I'll do is I'll give myself an executor. And I want an executor that will deterministically give us another thread. So what we'll do is we'll call it a cache thread pool. So this is just a thread pool that sits around waiting for tasks to get issued to it. And then what we'll do is we'll have the actual job that we want to run. And this is the guy here. Oops, that's not a B. That's just a callable service.
Completable future.
Okay, so what we want to do is we want to return a, So what we want to do is we want to return a completable feature. Completable feature is the unit of execution when we're thinking about asynchronous. When we want to execute a task on a thread pool, the computable feature is going to allow us to get there. And how do we get there? Let's see how that works. So I will use a var. I will call this guy here feature. And I'm not using Kotlin because you got to use the new keyword. And then what we want to do is we want to have the executor execute that. So we'll say executor dot execute, and then we'll give it a task to run. That task needs to do something like perhaps execute our audio utils, right? And we'll say audio util dot convert, and we'll give it the input file. So what's going to happen here is that input file there really represents a WAV file, and this WAV file will get output to another file
of type MP3.
Of an MP3 file. It's going to be an MP3 file in the future. And what we will do here is we will then return this feature. Okay, so what I just described here in this piece of code is the manual way to essentially kick off our completable feature job. Nothing here executes. This is all this is executed later on after it's scheduled. As you can tell, there is a closure in here. So once we handed that closure gets executed inside of a execution loop. And we're pretty certain that at some point in the future, we can block on it and we can wait for it to come back. Now, this is the manual version, but this isn't to show you that Spring can do this itself. So let's make Spring do this for us. How do we do that? This is very easy. We'll get rid of the executor. And what we want to do is we want to say async. We want to use the async keyword, and now we can start taking the executor away. So the first thing I'm going to do is I want to get rid of this whole execute function here, since I don't need it anymore. Since I'm using async, Spring uses a execution loop in the background. It gives us the whole event loop for us, and we're going to take advantage of Spring's own event loop. And while doing that, I can just paste this guy in here. I can say complete ed future, and now I have a completed future of the thing that I want executed. So remember, what Spring does in the background is it takes this async guy and it goes, okay, well, I'm going to give you a proxy that is a completable feature, and when the completable feature, the inner completable feature, that is the little nugget of the job that I want completed is completed, Springs will return, and it will give us our asynchronous function that we want.
So you're saying I'll be able to call this method from the perspective of a client, and it'll return immediately, even though clearly this wouldn't return immediately, right? If we ran your thing absent the
it's basically lazily evaluated if you look at it that way. It's not evaluated at runtime. It's evaluated as it executes on the job loop, on the event loop, or the executor thread pool. Okay, so we want to test that. We want to test how does this actually look like in a test case. So what we'll do is we will inject. So I'm going to inject this guy here, and let's see, it's called the audio service. There we are. All right, so what we're going to do is now that we have a task to execute, we can execute it in a test, and we can say something like val mp3 file, var mp3 file equals audio service dot convert. How do I get a file out of here? Let's try a value. And let's say that we have a value on our desktop. Who doesn't have files all over their desktop? I do. My desktop is dirty as heck. So let's say /home /desktop /sound.wave. I believe we have a file there, Josh. Yep. Is that right? Okay,
fingers crossed.
Yes. Okay, so we have a file here on our desktop that we're going to take. We're going to ingest that file, then we're going to convert it right, by feeding it to our Threadpool audio service converter. But what's more is we don't have, we want to basically introspect the state of that file afterwards. So how do I do that? How do I compose that stream of logic within Spring or within the computable feature API? And one way is we can say then accept. And what it'll do is it'll give us the ability to take a consumer, that is our MP3 file, because this is going to be the output of that convert. So if you think of something like map or take, or if you think of map or flat map, this is kind of like map that says, give me the result and I will do something asynchronous with that result. In this case, I'm going to use JUnit 5, or assert J, excuse me. So I want to make sure that the file exists, and also I actually want to make sure that this file has the same, .mp3 and get absolute path ends with .mp3. Okay, so this particular unit test here is all that we need to do to kick it off. We probably want to block on it. We could do really we could do lots of things. I can use a countdown latch. Probably don't want to use a countdown latch in this case. Okay, yes I do.
No, .get.
Where?
.get and then throw the exception.
Oh, excuse me, sir. Oh, but I wanted a countdown latch. Those are so fun.
Yeah. Bracket next to it. There you
go. Okay, there's a file there, right? Right. Tell me that there's a file there. Okay, good. All right, so that's it. That's the file. That's what happens here. Once we executed our async loop, you understand that I have to use get basically blocks the thread. You can use a countdown latch as well. So you can say countdown latch countdown, await the countdown latch to countdown, and eventually it will run and leave the main thread. In this case, it did exactly what we wanted to do. We were able to effectively hoist a process up into a thread pool, and that's really good behavior.
Now, and that got us further than we were before. At least we didn't have to manage low-level threading. But I think we can agree that low-level threading primitives are only going to get us so far. In this example, as interesting as it was, we only did one thing, right? We moved a file, we converted a file from a wave to an MP3, and obviously that's one of those things that, once you've started the process, you're done with the process, right?
Yes.
Sorry. Let me turn this way. Okay. So what we want to do now is we want to actually look at, we want to take a different approach, right? We want to see if we can move beyond the point where we're actually dealing with low-level threading primitives. In this example, we use low-level threading primitives, and Spring took away some of the work, like you just saw. We were able to get rid of the manual executor and all that stuff, which is cool. We can delegate to Spring to manage all that for us. But I'd like to get to a point where we don't need that. So we're back effectively to square one, right? We need concurrency, and we need the ability to evolve state in a safe way. We need structured concurrency, right? We need some way to safely change state, right? So structured concurrency is not a new idea. It's a broad term to describe all of the different approaches to concurrency that aren't the API equivalent of the Wild Wild West of YOLO, right? So things like runnables and executors and so on. We want to move, if we can, beyond that and let Spring do the hard work of running our code. So we can use structured concurrency paradigms like CQRS, like staged event-driven architectures, and like...
what about actors?
No actors.
Don't like word count?
We like actors, but we just don't have enough time. So that could be definitely the sequel to this particular talk, okay? So we're gonna look at other things. Now, we're gonna look at, how to manage the complex distributed state in a multi-node system, right? Managing that kind of state is difficult, but we can use messaging-centric control flow mechanisms because they're a natural way for services and systems to communicate in a multi-threaded and distributed environment. There's a great blog by Martin Fowler that talks about some of the possible applications of messaging, right? That's this blog here. And this blog is from February of 2017, so it's creakingly old at this point, but nonetheless, he's got a number of different use cases that he outlines. One, of course, is assuming the presence of messaging, you've got the event notification pattern. Here, one node communicates the fact that something else has changed through an event. They don't communicate what has changed, merely the fact of the change. And then it's assumed that the system of interest that is consuming that message would then requery the source thing for the actual information about what changed. So, for example, I might get an event that says, "Hey, the customer the number of customers has changed," right? And then it's up to me to query this to query the thing and then compute the delta myself. That's interesting, right? That's interesting. Another possible application is event carried state transfer. Carried state transfer is it's the opposite of what I just talked about, right? Instead of communicating just the fact of the change, you communicate the change itself. So in this case, you're sending the actual delta in the message payload body. Obviously, when you do this, you run the risk of having slightly more bandwidth being consumed, or possibly a lot more bandwidth being consumed. But again, this has the effect of not needing all these satellite systems to query the source system. They can compute their own view of the system as they need to based on the deltas that are carried or communicated in these event-carrying state transfer messages. And that feeds very nicely into event sourcing. Now, event sourcing is this idea where whenever we make a change to the state of a system, we record that change as an event, and we use something like a stack, something like GitHub, right, where we can version, or we can create a running list of changes that have happened. And if we want to recreate the state of the world, we can just replay the messages in that event source, right? So that's a very convenient thing because now you have a principal source of truth, and the system state is derived purely from that, right? Very, very powerful if you want to replay, etc. And there's a lot of other, that pattern rather, it leads very nicely into command query responsibility segregation. Now, this is the notion of having separate data structures for reading and writing. CQRS isn't strictly speaking about messaging. It doesn't imply messaging, but it works best with messaging. So all of these patterns, really, if you want to use them and if you see them in the wild, they're going to be using messaging. So I think messaging is a great thing for us to take a look at. And we're going to use Spring integration to do that. Okay, so we're going to build a new application. Again, going back to our
start.spring.io.
Exactly. Sure, no problem. Thank you. So we're going to go back here. I'm going to build a new application using the Spring initializer. We're going to say integration, and we're going to build an application that takes advantage of Spring integration. Now, of course, I'm also going to want Lombok. Now, Lombok is going to give me a library that I can use. So I'll use Lombok. I'm going to use Java 11 or 14, both of which are fine choices. Whatever you do, don't use Java 8.
How about using Java 8?
No, it's not a thing.
Don't make the house out again.
No. Okay, so hit generate, and we're going to hit generate and open this up in our IDE. Let's goodbye to that. UAO integration. Voila. No wonder.
It's actually loading, but
I hear the fans going. I'm like, is that actually Slack? It is Slack, and I don't like that. Goodbye. Oh, do you hear that?
Well, we like Slack. It's just the CPU does it. Yeah,
my CPU is not happy. Okay, so integration application, and what we're going to do is we're going to make this a little bit larger. I hope that's enough, suitably large, and we're going to expand the screen here just a bit, and we're going to build an application that uses the Spring Integration Framework, which is a pipes and filters framework, right? It builds upon the patterns espoused by Gregor Hoppe and Bobby Wolf's seminal tome, Patterns of Enterprise Application Integration from 2004, which is, by the way, a page turner. It's an absolutely marvelous book. Read it to the kids, read it to yourself, keep it by your pillow at night. It's an amazing book. And in that book, they talk about how to string together components that are fairly functional in nature. They're discrete components that accept messages in and they produce messages out. And so you can connect these components implicitly using channels, or sorry, using the DSL, or explicitly using message channels. So Spring integration lets you deal with both if you like. We're going to take advantage mostly of the implicit mode. So I'm going to say that messages will come into my integration flow on this publish subscribe channel. And when I say message, by the by, what I mean is an actual object called message, which is an envelope object that has a payload and some headers. Okay, so there's my two different types there, my two different channels. And now we can get back to the business of the messaging flow itself. And we're going to say when a message arrives on this channel, and we'll see how those messages get put into that channel just shortly here. When they arrive on this channel, we want to then handle them. And the first thing that we're going to handle, the first thing we're going to do to handle them is to use some support in a library from Spring Integration called Spring Integration File. So Spring Integration, because it's charged with integrating with the larger world, provides adapters, things that you can use to talk to the outside world, be it a file system or an FTP service or Twitter or TCP or MQTT or whatever, right? So I've got Spring Integration's file support on the class path, and I'm going to use the outbound gateway here to write data that I see coming into this file into a new directory, right? New MP3 directory. I'm going to call this new file, and I'll just say system. Apparently I've never done that part before. So desktop MP3s. Okay, so that's just a desktop folder, and all we're going to do is we're going to say whenever a file comes in that's a wave, we're going to move it to that new MP3 directory. Voila. And we want to make sure that if that directory doesn't already exist, it gets created for us. That makes life a little bit easier. And then from the handler, we're going to then do some transformation, right? So here I'm going to say transform file.class file, or actually wave, and here we're going to call audio util. So I need to copy and paste the same class that Mario just looked at in our last example here, and we'll just use that. We're going to depend on it, and again, just ffmpeg. We're just shelling out to the command line. That's not particularly interesting, but it is verbose, so we are going to save ourselves a few keystrokes there. Save the turtles. Okay. Audio utils.convert wave, voila. And then the last thing I want to do is I want to make sure that this has a name. So I'll say spec.id. I want to give it a name, and we're going to see that we need to reference this name later. Okay. So I'm going to give it a name, waves to MP3s, WTM. I don't know. I could type it out loudly, or longly, or whatever, but I don't know what the point is. Okay. Now, from there, I have the data. I've transformed it. I want to now handle it, send it out onto the MP3 channel, right? And once I've gotten that done, I have my entire flow. Now, I can use this code. I can literally just inject a reference. I can use a qualify annotation to get a reference to the Waves message channel in my code, and that would work just fine. But Spring, again, what we're trying to do is to show you how you can build complex messaging-centric and potentially concurrent threading applications while hiding a lot of that complexity thanks to Spring. And so one thing that should hopefully be clear here is that anything that flows through these messaging channels could actually be on a separate thread. There's no reason that this pipeline all happens in the same thread. This pipeline might actually involve different thread pools and so on, right? So I'm okay with that. I'm okay with what we've got here out of the box. And I'm not okay with not taking the opportunity to convert to a method reference when I can. So thank you, IntelliJ. What I'm going to do now is I'm going to hide that complexity. I'm going to abstract away that complexity to make it more approachable using a Spring integration gateway. Okay, so Spring integration gateways are a pattern, again, from that amazing book. And the idea is that you have a messaging gateway annotation. And I'm going to say that when somebody calls a method on this interface, on an instance of this interface, when they call that method, they're going to get a completable future, which will correspond to the actual messaging flow, the whole messaging pipeline. So, oops, I did it the wrong way around. I did it wrong. Okay, here, there you go. So the request, no, it's the other way around. I was right. Request, there you go. Reply channel is going to be integration application dot MP3s. The request channel will be integration application dot waves. Okay, so that can go here, and this goes there. Voila. Okay. Now, my friends, we have a pipeline. We can transcode the data, and we'll get a completable future. So again, when somebody invokes this method, because the payload is being sent in on the Waves channel, it'll eventually end up here, and the whole pipeline will get kicked off, and the conversion will happen asynchronously on a separate thread pool, or indeed a separate service, right? Because again, you can use channels and Spring Innovation to communicate messaging through Kafka or RabbitMQ or whatever, right? And so there's no reason that the message that starts in this flow has to end in this flow. It could conceivably leave our process altogether and get sent to another Spring Innovation flow on some machine that's just waiting to take the work and then finish it and then send a reply.
Purely distributed.
Right.
Yes.
So, okay, let's demonstrate that. Let's create a simple client here, a little listener. That's a good idea, a listener. Application listener. And it's going to listen for the application ready event, right? And this is just going to be oh, Josh, you can spell. You can do this, Josh. Look at me go. Okay. And what we're going to do is we're going to say when there's an event, inject the audio service here and invoke it accordingly. So, okay. Now the MP3, the wave is in the same place as the other one, the MP3 directory, basically. So I'll just cheat a little bit, copy and paste when you can, save yourself a little bit of pain.
There you go.
Sound.wave. This is actually a wave file. Haste makes waste, friends. Never type too fast when you can type just enough. Okay, so transcode, and that'll give me a completable future. And at this point, just to prove it's working, I'm going to get the results and log it out. Now, of course, the squigglies tell me I have an error. So throw new runtime exception, and exception. Good. So I'm just logging it out, and that'll give me the result. I'm just going to print out the result. I'll say file.getAbsolutePath. Okay, there you go. There's my get absolute path. That's redundant. I don't need that extra.
Yeah, second one.
Yeah, thank you. Okay, let's just
clean that up.
Ding. New file. Okay, now let's run this and see what we get. It should, if everything's gone to plan, work. Fingers crossed, huh? Okay.
Is it compiling?
It's compiling. It takes its sweet time to compile.
Okay, I hear the fan.
Okay, look at that. Converting. And converted. So it started up, and it did the right thing, and it's working. Now, I want to test this, right? You can see converted here, right? And there's the affirmation of the resulting file, So it did the work for us. Now, I want to test this, so I'm going to comment this out because I don't want the client to run during the test code. And we're just going to go to our test context. And again, we've got this complex, potentially involved moving thing called our Spring Innovation flow, and I want to now test it. So remember, in Spring Innovation, it's a pipes and filters architecture. So you have a lot of moving parts, but they're all bound by these little functional components that take messages in and that send messages out. So really, if you want to swap out any one part of the flow, then you can do basic testing, basic state-based unit testing, where you say, hey, the output of this pipeline component is as I expect it to be. So really, we just want to test the business logic between the inbound adapters and the outbound adapters, the things that originate messages and the things that terminate messages, right? The things that take messages from the outside world and the things that send them to the outside world. So the business logic in between, that's the stuff that we write. We don't care about how bytes get written to an FTP server. That's the outbound adapter's job to do. But we do care about everything right up to that point, right before it leaves the JVM and it's out of our control. And so Spring Innovation gives us some very interesting support here. Spring Innovation test is a test slice that you can use. It gives you a mock integration, and we're also going to inject the application configuration itself, and we can use that then to kick off a pipeline. So I can say this.application.waves, that's my message channel to which I'm going to send messages. We can use the gateway, but let's show the message itself, the lower level approach here. Wave file message, okay, equals message builder dot with payload, and I'm just going to take the name of the MP3 that I just painstakingly wrote out long form in my example. Goodbye. Take that. That's my file, and keep it consistent. And so we're going to create a message there, and we're going to say with a payload of type wave, and we're just going to call build. So that's my message. And now I want to send the message into the channel. So I'll say, okay, waves.send wave file message. And that is in theory all you would need to do. But again, that would actually invoke the pipeline. So what I want to do is I'm going to swap out the pipe. I want to swap out the actual conversion service bit, the message handler. And we can do this using the mock integration context, the mock integration class, which gives us the ability to mock a message handler. And here I can say, okay, given a new result, let's log out the results. I'm going to say, given the result, assert dot true result dot get payload instance of file, and assert that once we know it's a file, I want to prove that the string has an MP3 bit in there. So get absolute path dot contains MP3s, right? Yeah. There you go. Cheers. Okay, so there's our mock message handler. Message handler. And all I'm going to do is I'm going to swap out. I'm going to use this very convenient thing here, mock integration context, right? Dot substitute. No, I want to use the integration context. Where is that? Mock integration context. That's what I was looking for. So there we go. I'm going to use context. I'll say this dot context dot substitute message handler for, and here that name that we gave to that particular transformer, to that particular message handler earlier on, that pays off. So I'm going to say swap out that particular flow with this new message handler instead. So here's kind of like I'm mocking out that one thing, and now I can poke at the results that come back. Let's run this test instead of running the actual application.
Okay.
Go. All right.
Great.
So it worked. We see it works. Obviously, this is very powerful. Spring integration is very powerful. It's a great way to build highly concurrent, highly scalable systems and services. Obviously, Mario and I love Spring integration. We wrote a book back in 2011 called Pro Spring Integration on the topic.
That was fun.
Yeah, it was a lot of fun. I had fun, buddy. So that's cool, right? We've got our integration application. I like Spring integration, but I think we can do better, right? Or at least we can get more scalability if we embrace reactive programming. So reactive programming gives us a consistent paradigm with which to describe potentially latent, potentially unbounded streams of data. So what we're going to do is we're going to build a reactive application now.
Scalability, it will intensify.
Right. Yeah, right. So let's do that. Let's build a reactive application. I'm going to shut down this one. And instead of using Spring integration, we're going to go back to start.spring.io. I'm going to take advantage of reactive programming. Now, reactive programming is an inversion of the normal approach that we take when we build systems. Instead of pulling data from the producer of the data,
you just disappeared.
I just ghosted out of existence there. Instead of pulling data from the producer of the data, we're going to have the data pushed to us. And by doing that, we assume a new paradigm. We assume a new inverted flow where now everything is reactive, and if everything is reactive, then you can take advantage of alternative approaches to, for example, input and output, asynchronous I/O. This gives us the ability to free up the threads that we're not using. So instead of waiting on the thread for data that's not going to be here, we can instead unblock the thread, right? So I am going to use RSocket. Now, RSocket is a binary protocol that was forged in the fires of Netflix and Facebook, and it's a binary protocol. It's a non-blocking, natively reactive on-the-wire protocol. It very well integrated into the Spring ecosystem. You can use Spring Security, you can use Spring Integration, you can use Spring Data, all that. Spring WebFlex is a brand new reactive HTTP web stack for that. You can do WebSockets. So we love reactive programming in the Spring ecosystem, and wherever possible, we also have support for RSocket. Now, I have a book I just wrote actually that just got announced. It's just today. It's called Reactive Spring. You can buy that if you're interested, and we have a whole long discussion of that. Or if you don't want to do that, go watch the video I just released a few weeks ago, 2 weeks ago or so. It's called the Reactive Revolution, the RSocket Revolution, and it's on YouTube, and it's just out there. It's like 38 minutes, whatever. People seem to love it. It got 30,000 views in the first few days, so maybe you'll like it as well. So what we're going to do is we're going to build a client and a service that's going to be using RSocket, this binary protocol, and it's very simple. The component model in Spring makes it super simple to create an endpoint. So I'm going to say messaging endpoint greetings. And keep in mind, friends, that I'm going to do all of this in the same code base just for ease of demonstration and getting this done within the time that we've got. But that said, these are obviously going to be a client and a service, a requester and a responder. So you would normally have this in separate code bases, right? So request, okay, make the code bigger, and obviously you would separate these into two different code bases. So greetings request, greeting response, and the response is going to be a message that's informed or defined by the data in the request. And that request is just going to have a single name. Okay, so Spring private string name. There we go. Now, in the service side, I want this application to return an infinite stream of greetings responses given a single greeting request. Okay. So I'll say request, and I'm going to just return flux.fromStream, stream.generate, new supplier, greetings response, new greetings request, hello, request.getName at instant.now. That's the infinite stream, and if I were to run this as is, it would very quickly roll out, scroll down the floor and out the door. So what I'm going to do is I'm going to delay the elements that I'm seeing there just a little bit. I'll introduce time, which I can do thanks to the reactor scheduler. So that's my whole thing. That's everything I need to get a component model up and running. Obviously, you could tease this into a separate class if you wanted to. The only other thing that, in terms of configuration, that you need to do, and I'm doing this here instead of the config file because we have everything in the same code base, and I only want one side of the exchange to be a service. I'm setting the property, spring.rsocket.server.port, and the property is going to tell it which port to expose at RSocket service. So it's going to be in port 8888. And that's it. That's the entire service. Now let's go back to our client. Come on, client. Here's our client. No, that's
a response.
That's a response. Yeah. Okay, here we go. Client. Okay, bigger. And we're going to make a client that creates a reactive RSocket requester. This is the in RSocket, when a client connects to a service, they're not really client and service, right? I think about them like that logically, but really at no point is one dependent on the other. Once they're connected, they stay connected through the life of the application, first of all. And second of all, once they're connected, either side can initiate the conversation. So what I'm going to do is I'm going to create another bean here that's going to be an application listener. Now this service isn't this JVM process isn't a service, and so as a result, nothing is going to keep it running once the application starts up. So I'm going to use system.in.read just to keep the thread going, right? And I'll say, okay, return event, and when I've done that, I'm going to inject the RSocket requester here. And I'll say RSocket requester.route greetings, right, with two E's. If you can spell, I certainly can't. Data is going to be a new greetings request, and I'll say Spring 1, 2020. And then the response I get back will be a greetings response, right? So greetings response.class. And then I'm just going to log out the result. I'll say subscribe and print out each result that I get back.
Thank you.
Thank you, sir. Thank you. Okay, good. All right, now we've got our typical client. That's how you use the RSocket requester. I like this style, certainly, and it's very common. But Mario and I built a little project you might be interested in. It's an experimental project. I don't mean to imply that this is yet GA, but it's in the GitHub org for the Spring projects experimental, and you can use it now today. It's in our snapshot repositories. So it's called RetroSocket. So you just add this to the class path. Right, and it's an RSocket. It's a declarative RSocket client. So you just add this to the class path, get the repositories, add that to that. Command-Shift-R. That's my keyboard to re-import Maven dependencies, since I do that so often. And now we can build a different client. And here I'm going to say RSocket client interface greeting client. Okay, and here I'm going to create an endpoint. So this is the client perspective of the downstream service, but I'm just creating an interface kind of like what we could do with Spring Cloud Feign before, right? So we're going to create a greetings response, greetings request. Okay, so that's the interface. That's the entire thing. Spring RetroSocket will do that for you. It'll create that interface for you. So now we can create a new thing. We can just say, do that, and that, return event. Okay, and here I'll use the greetings client. Okay, client, and I'll say client.greet new greetings request spring 1 2020.
Yeah,
works just fine. Subscribe system dot out print line. Okay, so there we go. There's the entire flow, much simpler, I think. And now you've kind of hidden the complexities of dealing with a low-level communication. So let's run this again.
Okay, so this client just runs, and you're saying that this client will automatically get rewired so that it knows which RSocket endpoint to hit.
Right.
Yeah.
It knows which. It'll use the only one available.
Okay.
Oh, I forgot to do the important bit. I need to enable
RSocket clients. Yeah.
Right. There we go. Like, I forgot something.
Yeah.
Okay. So it'll automatically discover the first RSocket request in the context, but there's also in the documentation. If you go to the documentation, there's also documentation on how to pair a particular interface with a particular RSocket responder.
Nice.
Okay, there you go. Look at that. Multiple responses coming back over the wire. This is now a reactive stream being communicated over the binary protocol. Remember, HTTP doesn't understand true back pressure, which is critical when you build reactive systems, but RSocket actually has that. So there's some interesting possibilities here. You can do
you can do load balancing through the RSocket requester,
right.
Which is amazing.
And resumption and all that stuff.
Yes. So the RSocket requester is the thing that actually does the heavy lifting.
Right.
It's the syntactical sugar that RSocket, that RetroSocket gives us.
Right. Now, let's try a quick test and see how that all works. So I'm not going to use the Spring Boot tester. We're just going to do this the old-fashioned way. var server equals new Spring application builder dot sources, and this is going to be the service application, right? Dot class dot build and dot run. So it'll give me. I should have two application contexts. But the other thing is I need that property, don't I? I need the property on which to run the service. So here's this. Okay. Come on, test. Oh, okay. Properties equals 8888. Or I can just copy and paste all this. That actually helps me out.
Yes.
Client.
So build two new Spring contexts, one for the client, one for the server. That way you can isolate the server and client. It knows what to connect. One will be done before the other one needs to spin up. Therefore.
And what is it called?
Greeting client.
Oh, I didn't make it tight. I need to make that public. So you can see we've done this a couple of times so far. We've actually created the gateway and Spring integration. You saw when he used @async, that made it very easy for us to create a client representation of the complex concurrency happening behind the scenes. And now again, with RetroSocket, we can hide the complexities of the threaded code, multi-threaded reactive concurrent code.
Yes.
Did I make it client? I didn't make it public. I was talking and I didn't even do the thing I was supposed to do. So greeting client dot class. There's this, right?
Okay, so we got your being.
Greet.
Yes.
New greetings request spring 1 2020 dot now what this gives me is it gives me a reactive stream. Now I could do something I want to make sure that I can poke at this asynchronous value. Here I can use the step verifier. This is a nice thing in the reactive world. So I can say, okay, expect this infinite stream of values to just produce, I want just one value, so I'll take one. And I'm going to say I want to verify that it completes successfully. But before I verify it, I want to assert certain things about the results. So I'll say r.getMessage.contains, well, spring 121 or spring 1 2020, right?
Yes.
There you go. So that's the step verifier. Very useful for all reactive applications, not just RSocket.
Yeah.
We just happen to love
I love the step verifier. It's my favorite component.
Okay, look at that. Hopefully.
There's that Nyan cat. It's starting. That Nyan cat was there.
Failed to bind. Am I already running something?
Oh, okay, you can't bind.
Oh, my service is running.
Yeah. Okay.
Come
your
on.
test. Yeah.
My test instantiates the thing.
Yes. Okay, let's run again. And that's probably why we're seeing the fan go up.
Right.
We have threads.
Something, I think I left something running.
I think you left Slack
before we
running in the
started?
background. Yeah.
Okay,
Okay, so that's good. We ran.
Okay,
Green
so
light.
let me find whatever I was running before this application started, before we started our presentation. Something.
Oh, don't worry about it. Just,
okay.
Just know that your friend hates you for the next 10 minutes.
Okay.
We'll kill it. I thank you so much. That was awesome. Reactive programming helps us decouple other things and stuff. We like that. The only problem, of course, is that in order to maximize your investment in reactive, basically you have to program everything in reactive. And if you already have, your workloads are already programmed in Java or Kotlin, even, then that means that you're going to have to adapt those workloads to Kotlin and Java and recompile them and redeploy them, and possibly introducing bugs. You don't want to always do that, but Spring integration will actually help you meet there. So if you do have processes, you don't have to recode anything. Spring integration will allow you to adapt your current existing processes without rewriting your code. All that you have to do is write the necessary adaptation layer, and that's it. However, you can connect things that are necessarily you can connect things that are not necessarily threaded or reactive, although potentially you're going to lose some scalability through using the integration piece. So be careful when you use that. Now, the problem with Spring integration or reactive is that it does require the DSL. Like I said earlier, you have to readapt your code. But on the other hand, that might not be approachable, and you might not be accustomed to it because of imperative programming. We love imperative programming. We want to get back to the good old days of programming imperatively without having to think about threads or thinking about nodes or scheduling things. So what we do want to show you is something called the coroutine extensions for Kotlin. That is, Spring Webflux has coroutine extensions that I can show you here really quickly. And I think it's a really cool thing to show because it says that you don't have to code, you need more than you already know, and you can take advantage of threads.
Again, hiding that complexity. No hyphens, it makes weird packages.
So we're going to use Kotlin, and then we're going to call this code tests. And yeah, we got the same thing here. We want Webflux. Because we're using Kotlin, we don't need Lombok. If you know Kotlin, Kotlin is already the ultimate form of what we want in our JVM programming languages, unless you run Scala, and then you already have it there. But in this case, I'm using Kotlin, and I love Kotlin. So we'll go with that. If you're already used to using Kotlin, you probably know what I'm talking about with coroutines. But just for this particular example, I want to show you what that looks like in terms of Spring Webflux and how it gives us the ability to write imperative code without going too far into any sort of weeds, such as the integration weeds, threading weeds, or even the reactive plane. So I will write a really simple looking class. This will take about a minute to write, and then I will demonstrate how it will give us the enhanced ability of reactive threading without having to engage the reactive threading. So let's do that. We need that code. I want to see that code. Okay, so this is a Spring boot application. Basically, what I'm going to do is I'm going to take this application. I'm going to say, you, sir, are going to be a companion object. And we want that companion object to have a JVM static main, of course. So that's JVM static. Now I can give my bean and I can say, okay, so this is a particular router. I'm going to create a small little class here, and I'm going to call it user. Let's do two things. Let's first create a data element called data class user, and we'll give it an argument. We'll say ID string, and we'll say that it has a name, and that name is also a string. So that's simple there. And then we want a class to dole out users. So we'll call it user service. And we'll say that one method is suspend function. So suspend is the thing that gives us our ability to hoist our methods into reactive loops. So we'll get by ID. We'll say give me an ID and it's a string, and I'm going to return a user Spring 1 2020 is its name, and that's it. So it's a normal class. If you notice, it's imperative. I don't use any of the reactive things, but what I will do is I will make it reactive in a second. So what I want to say here is we want to call it router. So the function router, and this router takes a argument that's going to be our user service, and I will need to annotate that service, of course. And instead of using normal, I can do route. If you notice, in the past you use router, but with the coroutine version, we use something called corouter. And corouter is the thing that will hoist our router methods into reactive loops without us knowing about. Well, we'll know about it, but that's as explicit as we can get without actually having to write the stuff ourselves.
That service that you created, in this case, it's a silly example. We're just returning a value. But the point is, you could be talking to a reactive SQL database or a reactive NoSQL or whatever, get a result back, and return a coroutine value. So it looks like imperative code. It looks like you're actually getting a user, but in fact, you're actually getting a thing that will pause the thread behind the scenes, right?
Yes.
Okay, so
I will use this method called body value and weight, in which.
Oh wait.
Thank you. Okay, so we're going to use body value and weight, and all we're going to do is take our user service and get by ID, and we'll say rec.query param, and that query param must be some sort of a string, and we'll call it ID. And I, of course, missed that, but I'll put that back in there. So body value and a weight, and return. There we go. Hi. This is a
pattern parentheses to be there. Yeah.
Where do you see that?
Take the one from the right and put it on top of the.
Oh, thank you.
And get rid of the second one. Now, okay. I don't know if you need.
I don't need the user class in here.
Yeah.
Yeah, I can get rid of that. What's your deal here? Rec.query param. Oh, but .get. It's going to be a or else. This gives us an option. So options are awesome. I love options. It's going to be 1, 2, 3, 4, 5. That's going to be our default ID. So if we want to get an actual parameter, the option is saying that I can either throw in an exception or I can just give us a default ID.
You're doing a path variable.
That's oh, yeah.
Not a query parameter.
Yes, of course. Okay.
Now I get why I'm confused.
Ah, okay. I see what you mean. So path variable. Okay, so now I don't need this anymore. Okay. Okay. So delete that. Okay. So now we have that. That's a standard method. We could test this, but we're going to run out of time.
Right.
So what I want to do is show you that this corouter here is a thing that will hoist us up. If we were to write a quick unit test, it would look like your normal one. Let's just run this. Let's just execute this itself.
We have to run the last slide.
Do you have HTTP?
No. Probably, yeah.
Yeah, you do.
Okay.
Okay. Hi. Server is running. Okay, we're on port 8080. So what we'll do is we'll say by ID /1234556. Okay, so cool. Not found, of course, because it's not all. It's I said by ID and yet I called it all. Okay, so that's cool. So that's the thing that we want. It's remember this is purely reactive now, but all I had to do was add corouter to an ordinary request server response, which is really cool. Very little work done there on my part.
That's awesome. We've come a long way. I think that as a result of what you just showed us, we started with low-level threading in the ecosystem, and then we've moved all the way to the point where now we have completely decoupled our service and
decoupling intensifies.
Right.
Yeah, and so decoupling will kind of turn us into the Star Trek Enterprise. Everything is something else, and especially when
something
boom happens. Of course.
Thank you, everybody, for your time. We're happy to answer any questions. We're going to go to the Q&A room, I guess.
Yeah.
From here.
Yeah. Thanks a lot, everybody. This has been really insightful. I hope for you. It's been a wonderful moment. And enjoy the rest of the conference.
Thanks, bye. Where's Bob? Without Bob, we're lost. What's the point?
Yeah, that actually was good. No, the thing is,
Josh, Mario, thank you. As always, you both have such a depth of knowledge in all of these things. Bootiful, #Bootiful. And so thank you for sharing just a skosh of that that deep well that you have. And they have a Q&A set up right after this. So if you're not quite done with your Spring One experience, head on over to that Q&A. Go to the Spring One Slack channel. There's going to be in the beginner-friendly Slack channel, there will be a Zoom link that you can go and ask Josh and Mario your questions. We can't thank you enough for tuning in to this channel, beginner friendly. If you were with us the whole time, or if you're jumping back and forth, we just thank you for sharing your time these last 2 days. I also want to thank Bryant and Lowell and Mike and Tasha and Catherine Efert and all the people on all of the production side of this. This was a fantastic 2 days. And I want to thank you all for tuning in and learning so much, as well as bearing with some of our little technical difficulties and our roommates coming in and bothering us while we were trying to present. So anyway, I've been Bob Brindley. Thank you so much, and enjoy the rest of your afternoon.